Alright, welcome back. We are still talking about the continuous time Fourier transform and its properties. This is the last video for the properties, so let's take a look. I saved the best for last. Alright, so I just want to talk about two properties today, the convolution property and the multiplication property. So I'm not going to prove these. I instead want to interpret them and demonstrate to you why they are so important. So for convolution, the convolution property says that if x has Fourier transform capital X and y has Fourier transform capital Y, then the convolution of x with y, we might be interested in, hey, well, what's that Fourier transform? So we have a signal who's the convolution of x with y, and it turns out that that signal's Fourier transform is the multiplication of capital X with capital Y. So that is to say, the operation of convolution in time is the multiplication operation in frequency. So this is amazing to us because convolution, convolution is important to us, and we spent a long time on convolution, and it turns out, well, you can sidestep convolution if you want. All you have to do is take the Fourier transform of the things that you are trying to convolve, and then just multiply them in frequency. And so let me remind you that we're talking about engineering, not just math, engineering. So if you have a linear time-invariant system with impulse response h of t and input x of t, then the output is x of t convolved with the impulse response, right? And do you remember that we've been saying this capital H thing? Even before we got to Fourier transforms, we were calling this capital H thing the frequency response, and we said it was related to the impulse response, like this. Again, we said this way before Fourier transforms. Well, what is that? What is that equation? This is the frequency response. What is that equation? That is exactly the Fourier transform of the impulse response. So you see, this whole time, now we can finally appreciate it. The frequency response is the Fourier transform of the impulse response. Those are Fourier transform pairs, right? And so, we said all these good things in class in the first half of class about impulse response, how it tells us everything we need to know about a linear time-invariant system, and it turns out then its frequency response also tells us everything we need to know about the linear time-invariant system, being that there's a one-to-one relationship between a signal and its Fourier transform. So this is good news for us, because then that means if I want to find the output of a linear time-invariant system, I could do convolution in time, right? That's the way to do it in time. But there's another way, and that is to find the frequency response, which is the Fourier transform of the impulse response. Find the Fourier transform of my input, and then multiply them together. Multiply is the operation in frequency, and that gives us the Fourier transform of the output if the output was y. Okay, so that's how we can get the output in another way. This forms the second big result of signals and systems. Remember, the first big result was this, actually. And so now the Fourier transform of that equation is this thing here. And so I want to point out then, again, we have the multiplication of the input spectrum, the input frequencies, by this frequency response of the system to get the output. So if this frequency response is 0, or close to 0 at certain frequencies, then those frequencies that we're inputting don't get to the output because you are multiplying them by a small, maybe 0 number. So anything times a 0 number is 0. So that's the concept of filtering. Again, we see it here. It's this property that allows us to filter signals by their frequency. And of course, we've already talked about why filtering is so important. We talked about filtering when we saw the Fourier series. All right, so that's a big one. It's a big one for us. Now, another big one for us is going to be the multiplication property. So multiplication property is the dual to the convolution property, and it says that if x of t has Fourier transform capital X of j omega, and y of t has Fourier transform capital Y of j omega, and if I have a new signal that's the multiplication of two signals, what's its Fourier transform? It turns out that its Fourier transform is 1 over 2 pi times the convolution of the two transforms. That's the property. So why is that the dual? Because up here we said that multiplication in time was, or up here we said that convolution in time was multiplication in frequency. Now we're saying multiplication in time is convolution in frequency, and I'm going to give you an awesome application to this, and just a little bit of foreshadowing. Sometimes this property, multiplication property, is called modulation. The modulation property. Do you know what AM stands for in communication systems? Do you know what this is? Amplitude modulation. And do you know what the FM stands for? Frequency modulation. Okay, that's related to this property. It turns out this is the property that allows us to broadcast signals, electromagnetic signals, and I'm going to demonstrate that to you right now. I'm going to show you why that is by showing you an ideal transmitter and receiver. So it would work like this. Let's say we have a message m of t, okay, a continuous signal m of t, and it has Fourier transform capital M of j omega. And I'm going to draw the Fourier transform, and I mean, this is a message. I don't know what its Fourier transform looks like, but for sake of argument, let's just say it looks like a triangle because triangles are easy to draw. Now, any practical message will be band limited, meaning anything you see in any application is going to have the highest frequency and then no energy after that highest frequency. Okay, that's a band limited signal, and we would, since it's centered around 0, we would call this a baseband signal. Okay, so if I were, I'm speaking right now, if I were to record this and look at my Fourier transform of my voice, it would be a baseband signal, and it would be band limited because there's a certain highest frequency at which my vocal folds just do not produce any more frequencies higher than that. So there would be an omega 1 for my voice, but also it would be at baseband. There would be a lot of energy around the low frequencies, and then they would get higher, and then they would be cut off at that point. So this is like a typical message that you would want to transmit. All right, but as it is, you cannot transmit this over the electromagnetic spectrum, and that is because it's not at a high enough frequency. So there's a range in electromagnetics where you can broadcast things like megahertz frequency, for example. So this is not at megahertz. This would be something like, maybe this frequency might be like 20 kilohertz or something like that. Okay, so what I need to do is I need to take this message and I need to shift it up in frequency, but I need to preserve the shape of that message so I can get it back eventually. So the scheme here is to take m of t and multiply it by, we'll call it p of t, and that's going to be a cosine of, I'm going to call this omega c of t, and the c is not cut off. The c stands for carrier frequency here, and then I'm going to call this r of t at the output. Okay, so let's understand why we would multiply by a cosine of this carrier frequency, and I'm going to make omega c much larger than the bandwidth of my message, much larger than omega 1. So why would we do that? Well, what's the spectrum of a cosine wave? Well, we've looked at this before, right? So this has the Fourier transform is pi right there, right? So that was the, and this is centered at omega c, the carrier frequency. Remember that? So this would be p of j omega. This is the Fourier transform of a cosine wave. We've looked at this already. It's got half of its energy at a frequency omega c, and another half of its energy at frequency minus omega c. Now, when you multiply those two things together, okay, m of t with p of t, then they convolve in frequency with a factor of 1 over 2 pi. So now I need to perform the convolution of these two signals to figure out what r looks like. Okay, so that's actually very easily done. Remember, convolving something with an impulse is easy to do. When I convolve the right impulse with the triangle, the right impulse is shifted by omega c. So what does that do? It shifts by omega c. Right? Convolving anything with a shifted impulse gives you a shifted original signal. And because of the pi, or 1 over 2 pi, and here's a pi, this makes 1/2. And then for this impulse, when I convolve it with the triangle, I get a shifted impulse down here, right, at minus omega c, and its amplitude is 1/2. And further, because omega c is much larger than omega 1, then these two triangles do not overlap. So omega c is the carrier frequency. It's like 101 megahertz or something, some radio station you want to listen to. So because this is true, they don't overlap. The triangles don't overlap, which is going to be critical here in a second. Now, this is r of j omega. This is the spectrum of little r here after the multiplication in time. So this means now our original message, half of its energy, right? Half of its energy has been modulated up to the carrier frequency, and half of its energy has been modulated down to minus omega c. All right, and then it's this that gets transmitted now to this goes to an antenna. This goes to an antenna, and then that gets broadcasted. So this is actually an ideal transmitter. Okay, that's how an ideal transmitter works. And again, it's because of the multiplication property. Multiplying by a cosine in time has the effect of modulating the frequency content up. Now, let's talk about the receiver. Okay, the receiver now. What I'm going to do, so let's pretend in the land of leprechauns and unicorns that I receive the exact signal that was transmitted. Now really that would never happen, but we need to understand the base case first. so now I would take that received signal from my antenna and I would multiply it by P of t again. And then I need to do something, but let's see what happens when I take this signal now in the frequency domain, R, and multiply it again by this P of t. So again, P of t, I erased it. P of t has the spectrum like this, omega c minus omega c, right? Pi, omega. And so when I do the convolution here, I'm going to have 4 triangles because this thing convolved with both of these, and then this thing convolved with both of these. So let's call this signal, let's call this y of t. Okay, let's look at y of t's spectrum. Okay, I'm just going to create some space up here. Okay, so y of t spectrum. So this is omega. This is going to be y of j omega. So first of all, when I convolve this impulse by omega c, shifted by omega c, then this triangle is going to go up to twice omega c. So I'm going to have twice omega c up there, way up there. And then it's also going to, so yeah, that one convolved with that one is going to be twice omega c, and its amplitude then I have 1/2, I have pi, that's 1 over 2 pi, so I'm going to have, that's pi over 2, and then remember there was a 1 over 2 pi there, so there's going to be 1/4 the amplitude there. Then when I take this impulse with this triangle, that shifts up the triangle, the original message, to baseband, right? And so that's going to be 1 pi over 2 times another 1 over 2 pi, so that's going to give me 1/4 of the energy at baseband. Now when I take this impulse, which is shifted to the left, with this right triangle, or triangle to the right, that's going to shift this one back down to baseband. So I'm going to have 2 triangles with 1/4 of the energy, and so that means I'm going to have, they sum together to make half right there. And then when I take this left impulse and I convolve it with the left triangle, that shifts it down to twice omega c with an amplitude of 1/4. So this is the spectrum now of y of t. And if I listen to this, right? If I listen to this, these things up here at 2 omega c might cause some problems. And so I want to get rid of them, and so what I would do, they might cause some problems to my electronics and my amplifier. So what I would want to do is put an ideal low-pass filter here with a gain of 2. Why 2? Well, because I have a 1/2 there at baseband. So if I can do that, if I have an ideal low-pass filter with a gain of 2, then I have only this triangle left, right? Because these triangles are gone because they were low-pass filtered. And I have this triangle that goes through the low-pass filter, and a gain of 2 with 1/2 makes 1, and I'm back with my message signal, which I can listen to. I should have said at this point that R you cannot listen to because R's frequency content is way above human hearing, right? That we're talking about megahertz here to send over the airways. You can't hear megahertz. Your human hearing ends at about 20 kilohertz. So you can't listen to R the way it is. You have to multiply it by the cosine to bring it back down to baseband, filter all this junk out, and then listen to the baseband signal. So this is an ideal transmitter, receiver, right here. So I want to point 2 things out for you. Number 1 is when your instructor starts drawing these box diagrams, you want to consider how you would actually build these things. And you'll see these things in control systems and signal processing courses, communications. How do you actually build this? Well, you can build a cosine wave. You can build a circuit that generates an oscillator, right? And maybe some of you have done this in analog electronics, where you built an oscillator using an op amp, a negative feedback op amp, and some resistors and some capacitors and a diode. And how do you build the multiplier? Well, again, you can use 3 negative feedback op amps. Op amps are the key here. 3 negative feedback op amps to build a multiplier. Maybe you did that in analog electronics, maybe you didn't, but I bet in analog electronics you saw how to build a summer, an amplifier that sums two things together. Well, you can use op amps to build an amplifier that multiplies two things together. And then we've already talked about how to build the low-pass filter using an RC circuit. Now, the final thing I want to mention about this is that notice the transmitter and the receiver both need P of t. That is, they need to know the cutoff, or not the cutoff, the carrier frequency. So, the radio stations say, hey, I'm going to broadcast at 101.1 megahertz. And then you, if you want to listen to that, you also need to know that I'm going to listen to 101.1 megahertz, right? You guys have to be coordinated. The transmitter and the receiver have to be coordinated so that they know the frequency that's being transmitted and received. Awesome. So I hope you enjoyed that, and so I know I did. That's one of my favorite topics. And so in the next few videos, we're going to now look at some examples of how we can apply some of these properties. Okay, so stay tuned.